Welcome back. So this is the model that we've created, an efficient net feature extractor. Our input data for when we train the model is going to be images of pizza, steak, and sushi. We've got the efficient net B0 architecture, which we've frozen. It's pre-trained on ImageNet, so we're going to use those weights to find patterns in our own custom data. And we've also updated the classifier head layer here so that it works for 3 classes, in other words, pizza, steak, and sushi. And if we keep going, this is what we did. We started with this, a model that had all of the layers as trainable, and it had 5 million or just over 5 million trainable parameters. But then, what did we do? We updated it so that it no longer has all of the layers of trainable, and the output layer here no longer has 1,000 classes, it has 3 classes suited to our problem. And so, we changed the classifier head. We've got, this is the original, and this is the new one. We keep the features the same. Classifier head, out features gets changed. That's all we've done. Keep the features the same, change the classifier head. And we're left with this. Now, most of the layers in our model are not trainable because we set their requires grad attributes to false. But the output layer is trainable. And we've got 3 output neurons. And so we have a dramatically less number of trainable parameters. So hopefully our training should be quick. And let's test it out. We will create here. Section 4 is train model. So let's see if we can beat our tiny VGG results that weren't too good. So to start off, we will define a loss and an optimizer. The loss function is going to be nn.crossEntropyLoss. And the optimizer is going to be the faithful atom optimizer that we've used plenty of times. And we want to optimize our model parameters. We'll set the learning rate to 001. Shift and enter. Beautiful. We've got a loss function and an optimizer ready to go. Now, because we've imported the going modular scripts over here, we've got engine.py, which contains our train function that we created previously in section 5. There we go, train. This is going to leverage test step and train step. So let's import the train function from engine.py. Import train function. Or in fact, we'll just, from going modular, modular.goingModular, we will import engine. And then we can set the manual seeds, because whenever we train, we're going to leverage randomness to optimize our model. And we'll go torch.manualSeed 42 and torch.CUDA.manualSeed. We'll set that to 42 as well. Now we'll start the timer. These are steps we've seen a few times before, so we're going at a little bit of a faster pace now. So from timer to import default timer, default underscore timer that is, as timer. And then we'll set the start time equal to timer. And let's set up the training. This is so exciting. Our first transfer learning model, and save the results. So we're going to save the results to a dictionary, and we'll set engine.train to train the model. Model equals model. The train data loader is going to be what? The train data loader that we've created before. The test data loader is going to be the test data loader that we've created before. Then we've got our optimizer in the cell above, and we've got our loss function is our loss function in the cell above as well. We'll keep it nice and short, just 5 epochs to begin with. You could always train for longer if you wanted to. And then the device is going to be our target device. You see how beautiful it is? The fact that we can just leverage our train function now. That's only a few lines of code, and we've mimicked the functionality of what's in here. We've got all of this functionality by calling this engine.train. How beautiful is that? So let's now end the timer, and we're going to train our first transfer learning model. This is so exciting. This is my favorite topic in all of machine learning, transfer learning. And print out how long it took. So end time equals timer. And then we're going to print out a little info tag here. Info, and we'll go total training time is going to be the end time minus the start time. How do you reckon this is going to go? Let's place some bets now. Is the transfer learning model, the EfficientNet B0 trained on all of ImageNet, going to outperform our tiny VGG? Do the extra parameters help? So our model has 4 million total parameters, but only 3,000 of them are trainable. So let's see. 3, 2, 1. Have we got any errors? Maybe we do, maybe we don't. Oh, I've got a space there, do I? Oh, what happened there? Excuse me. We did have some errors. There we go. Training started. Oh, this is beautiful. Oh my gosh, already at 55. 81% accuracy on the test data set. 85% accuracy. 86% accuracy on the test. 88. Oh my goodness. We have reached 90% or nearly 90% accuracy in 5 epochs in 13 seconds on our pizza, steak, and sushi data. What? Now, just a reminder, don't worry too much if your numbers aren't exactly the same as what I've got. The trend should be quite similar, as in your test accuracy should be going up, your test loss should be going down. But don't worry if the numbers aren't exactly the same. That's due to the randomness of deep learning, and it will be quite random despite setting the random seeds, depending on the hardware you're using. So, does that mean we've beat our tiny VGG model with transfer learning? If we go back, this is custom datasets, section 4. Our tiny VGG ended up with about 20% test accuracy in, how long did that take? 65 seconds? Why did that take so long? Was that on the GPU? Oh my goodness. We just wiped the floor with our tiny VGG model. All with the power of transfer learning. Look how, all of these layers contributed to our model performing at nearly 90% accuracy. I would be happy shipping a model that was that accurate. But let's not take these values as numbers on a page. Let's keep going and evaluate our model. We're going to evaluate our model with plotting loss curves. So we've done this previously. You might want to go to here and go plot loss curves and look how we plotted loss curves in the past and give that a go. Otherwise, we have a helper functions.py on the GitHub with a plot loss curves function. So you might want to either import that into this notebook and plot the loss curves from the results dictionary, which looks like this, and inspect them. So give that a shot, try to plot the loss curves of our first transfer learning model, and we'll continue with the evaluation in the next video.